You see it?
Yeah, okay. Right, so our second speaker today is Claude Confort, who will be telling us about string diagrams for classical mechanics.
Thanks for the introduction. Thanks for the invitation, and thank you, JS, for suggesting me to speak. So I'm a postdoc in France. This is my super long affiliation. And I'm visiting JS at Macquarie University for 20 days, my last week. I've really enjoyed it here. And today I'm going to talk about this work, which I've done with my two co-authors, Robert and Titouan. Robert, who's in Edinburgh, and Titouan, who's just across the road from me. But the purpose of this talk is I don't really want to go into technical details, but rather to motivate the kind of field that I'm studying. So this is my kind of motivation. In physics, there's lots of things which are not fully formalized, or they're formal but not done in a very clean way. So I want to find something in physics and then turn it into a category, make it completely formal. And then what I really enjoy doing is to give a presentation in terms of generators and relations. So there's really three aspects to my research. One is physics, one is category theory mathematics, and the third is kind of more computer science, using rewriting theory and finding normal forms, giving generators and relations. So you can put things in this kind of triangle where you have physics on top, which is kind of this sometimes informal semantics. On the left is category theory, which is the formal semantics. On the right, I think of as the syntax, which is more like the computer science, to try to make this diagram commute in a sense, even though on the top it's not necessarily a formal thing. Yeah, and I don't have any training in physics, more theoretical computer science and mathematics. So the way I think of physics is just a source of examples for problems which I can solve, and then I have to go read physics textbooks to find examples. Otherwise, it's just esoteric. To me, not as interesting all the time. So this talk, I'm going to separate it into three parts. The first part is I'm going to talk about linear algebra, but in a way that probably none of you have ever seen before. So instead of using algebraic expressions to turn things into isotopies and graphical equations so that you can restate all of finite dimensional linear algebra, but just using pictures. And then the second part, I'm going to talk about a very, very basic review of Hamiltonian mechanics and symplectic geometry. I stress very, very simple, because I don't fully understand the more nuanced aspects of it. And then the third is I'm going to take this graphical description of linear algebra and this basic understanding of Hamiltonian mechanics, and then combine them together to get some sort of graphical language for very, very well-behaved, very, very linear mechanical systems. Yeah, so here, the first thing I want to do is informally introduce the notion of a symmetric monoidal category. So I'm skipping over many details, but you don't really have to understand all of the technical coherence things to get the point. So symmetric monoidal category is a category, so it has a class of objects, class of morphisms between objects. And since it's a category, you can take composites of things. And I've suppressed the identity. There's always an identity morphism on every object. And then the important part here is you can also take the monoidal product, which is kind of like a tensor product. And I've also suppressed the monoidal unit, so there should be kind of a trivial thing you can take the monoidal product with. Yeah, and there's a bunch of coherence isomorphisms, which are not so important. And all of you are familiar with examples of symmetric monoidal categories. So for example, take the category of sets and functions. This is a symmetric monoidal category in two ways. First, you can take the disjoint union as this monoidal product. And second, you can take the Cartesian product. So these are the two canonical examples in a sense. And the nice thing about symmetric monoidal categories is you don't need to know all of these coherent stuff. You can just, everything can be defined purely in terms of pictures. So I'll draw the objects as wires, where I'll put the label on top of the wire. And the morphism is just like a box in between wires. And for the rest of the talk, I won't draw the object labels just because it's annoying. And the idea is that the composite, you just draw by connecting things like in a line, and then the monoidal product, you draw things just by putting them on top of each other. And then what's really, really nice is all of the coherence axioms and everything of a symmetric monoidal category can be reduced to this like these isocopies. So you take the monoidal product, you can slide things past each other, and also you can braid wires. You can slide the morphisms past the wire, and then the symmetric part is that if you take the braiding twice, it's just the identity, so things don't get tangled. But basically, you can just do the things you would expect you could do by drawing these pictures. So I'm going to give an example, which will be like the foundation of linear algebra. So when people think about linear algebra, at least like in an undergraduate math course, they usually think of matrices. But for me, that's not sufficient because I need constants. So I need to talk of like about affine transformations or affine matrices. So just like for matrices, the objects are natural numbers, right? You have like n by n dimensional matrices, but the morphisms now are a bit more complicated. So you have your morphisms are pairs, where the first element of the pair is an n by n matrix. And the second element of the pair is a vector. So you can think of this as like the homogenized matrix of an affine transformation. And then the composition is just given by the semi-direct product. So you compose the matrices in the first component. The second component, you apply the linear transformation to the vector and then sum with the vector of the other thing. And then, yeah, there's an identity morphism, which is just the identity matrix, and then the vector 0. And then the monoidal product, you just kind of component-wise take the direct sum. So for the first two matrices, take the direct sum, and then you stack the vectors on top of each other. And of course, there's this monoidal unit, which is like the identity for the monoidal product, and it's just the number 0. And I prefer to do everything in terms of string diagrams because that's kind of like my motivation to see, for example, if we can reframe this categorical like algebraic structure just purely in terms of generators, like as string diagrams and equations between the string diagrams. So this example is like well known, I guess, or kind of well known in the literature or in folklore. So you can generate all of these affine matrices, these finite dimensional affine transformations using first this one generator, which kind of copies things. So the linear part is just the vector 1, 1, and the affine part is just 0. And then you have the kind of discarding thing, which is the 0 by 1 dimensional matrix. So you can have 0-dimensional matrices, and then just the 0-dimensional vector. And then dually you have this kind of addition map which sums things. So it's just the vector 1, 1, affine part 0. And you have this map which just kind of injects 0. And also for every element of your field, you just have like a 1 by 1 dimensional matrix, where just the number A, and then the vector does nothing. And also, so all of the stuff above is the generators for matrices, but for affine bits, we're going to need one extra generator, which is in the first component, the linear transformation is a 0, and the affine vector is literally just the number 1. And I won't prove it. The proof is very like elementary, but in a sense, because you use that to do row reduction. But all of these things generate every single affine transformation under composition and monoidal product. But generating all of the affine transformations is one thing, but another thing is to know what equations these things satisfy. Because like before, we gave things all algebraically, there's no real interesting equations, it's just, you just do matrix multiplication. But here, this like poses an interesting question. Can you reformulate this category just only using pictures and equations between them? And you can. So the first set of equations I'm going to impose is that this white thing forms a commutative monoid. And the second thing I'm going to impose is that the black stuff forms a co-commutative comonoid. And together they interact according to the bialgebra rule. And if you take any number, it's natural with respect to the black and white stuff. So you can just slide any number past all of this stuff, and this is kind of reflecting the fact that the field has a action on a module. And yeah, I'm going to impose more equations, namely that basically under convolution and multiplication, you get all of the axioms of the field of the ring. So if you take, if you copy, multiply by A, multiply by B, and then sum them together, then you get the sum. Zero is just like discarding and then inserting the zero matrix. You take two things, you multiply them. And one is just like a wire, the identity. And so all of the stuff before was just for matrices, and I just want to do everything with affine shifts. So the two more equations that you need to describe affine shifts is that if you shift by one and then copy it, that's the same as shifting by one of the two components. And also if you shift by one and then discard it, that's the same as just nothing. Yeah, so maybe I'll like give an example. If you like A, B, C, D. The idea is that this should be like the matrix which goes this A, B, C, D. If I haven't got it correctly, and then there's no affine shifts. Zero. So the idea is take some kind of well-known structure algebraically and then see if you can reformulate the definition in terms of pictures. Here it's kind of somewhat easy to do, but in general, this becomes really, really complicated. So to do linear algebra in terms of affine matrices, it's not really enough for my purposes because you can't express things like kernels, images, subspaces. So I'm going to describe a more expressive category so that it's like a nicer setting to do linear algebra. And this is the setting where the morphisms are now not affine transformations, but affine subspaces. So there's this symmetric nodal category, which I call AFREL, or affine relations. And again, the objects are natural numbers. And now the morphisms aren't affine transformations anymore, they're affine subspaces. So the morphisms are either the empty subspace of k to the n plus k to the m, or it's the coset of a linear subspace by a vector. So if L is a linear subspace, A is a vector, and it's the set of all of the vectors in V where you've subtracted by the shift A. And now the identity is just the diagonal relation, the diagonal subspace. And composition is relational composition. So if you have two affine relations, one from n to m and one from m to l, the way that you compose them together is you look at all of the pairs in k to the n plus k to the l, such that there exists some vector in k to the m where vu is in the first thing and uw is in the second thing. So you're like tracing out over the common intersection between the two relations to get a new one from n to L. And again, the monoidal product is the direct sum. It's basically that you would expect, and the unit is again 0. So now I'm going to do the same thing and give generators in terms of these string diagrams, modulo equations that just reformulate this definition only in terms of pictures. But first, we need to notice that there is a connection between affine matrices and affine relations, namely that you can take the graph of an affine transformation and get an affine relation. So given this affine transformation here, you send it to the subspace, which consists of pairs, where V is like the input vector in Kn, and then you just apply V to this affine transformation. This gives you a subspace of k to the n plus k to the m, which is like just like the graph of a function is a relation, the graph of an affine transformation is an affine relation. But also you can do things in the other direction, just by taking the converse of this relation. So you have an affine transformation from n to m. You can also get an affine transformation from m to n, where the order of the morphisms has changed. And you just swap the direction of where you put v and where you put a composed with v. So now now that I have this graph and this cograph, I can give generators and equations for this affine relations. And this was given by Zanazi and all in their paper in 2019, I believe. So the first thing I want to do is take all of the generators of affine matrices and their equations, but twice. So first the ones I gave on the first slide, and then I'm going to take the same things and just I'll flip them like this. So you have like your, what was before, you had a white commutative monoid. Now you're going to also have a white co-commutative comonoid, and same for the black one. And I'm going to impose that the black commutative monoid and the black co-commutative comonoid form of Frobenius algebra, which is this equation, and similarly for the white one. And these equations, so this is like saying if you copy something and then demand that the two things are equal, that's the same as the identity. And this is like saying that if you sum two things and then demand that this is the sum of the same two things, that's the identity. And then this is like co-discarding, and discarding is the identity, and then 0, and then imposing that something is 0 is the identity. And for any invertible element of your field, so any non-zero element, if you take the graph of that element followed by the cograph, or conversely, you take the cograph followed by the graph, that's just the inverse of your field. And what's really important about these Frobenius algebras is it kind of allows you to bend around wires. So there's 2 ways you can do them, one using the copying and one using the addition. And they're isomorphic to each other, but you have to multiply by -1. Because one is like a this is like a subspace. This is the subspace of pairs x and x, and this is the white one is the subspace of pairs x plus y is equal to 0. So to get the pairs equal to x and x, you have to multiply one of them by -1. And yeah, you need another equation for the affine stuff. And this is like saying that if you take the affine shift by 1 and then you require that it's equal to 0, well, this like destroys everything. It's nonsensical. So it kind of consumes the whole diagram and just makes it equal to 0, or makes it equal to the empty set. So this is a kind of unusual equation imposed by affineness, which just, you have something like this, it's bad, everything is destroyed, and it's just equal to the empty set. And I'm going to use this like special notation, which will be more useful later, called like spider. So if you have any connected component of these gray things, then you can kind of, I'll contract them to a normal form, and I'll draw them like a gray node with a bunch of inputs and outputs. just as a like syntactic sugar special notation. And similarly for the white things, except I'll give them like a label in case you have an affine shift and you multiply by something and then it's connected. So because drawing, like for example, when you have these cups and these caps, you could just forget about this thing, and you just have a cup just with a single white node, and without having to like draw this extra stuff all the time. Same for the black one. And for the Frobenius law here, you would just kind of contract them to a single point. Okay. And I should say, yeah, before you had matrices, but now you can talk about like images and kernels of matrices all within this language without having to go externally and to do some external argument about, you know, the kernel is the set of all of these things and so on. It's all lives within this syntax. So if I want to take the image of this matrix, I would just put these black dots on the input, and this subspace would be the image of this matrix. And dually, for the kernel, I would just put these white things on the output, and that's just kind of imposing the equation that the output is 0, which is what the kernel is. But I can do it with affine transformations as well, for example, when I have this label of 1. So all of my kind of argument is that you can do all of finite dimensional linear algebra using this category of affine relations. And moreover, you can just do everything in terms of manipulating these string diagrams and applying isotopies and these equations. Everything kind of lives in here and it can be reframed in this way in finite dimensions. Yeah, so this kind of transitions to the second part of the talk. That's just like linear algebra using pictures. And what does it have to do with physics? So this is where I have to give like a very brief review of Hamiltonian mechanics. So what we want to do in a way is to take these affine transformations, but refine them in a way so that the objects carry some sort of physically relevant structure, and the morphisms capture the equations of motion and Hamiltonian mechanics. So I want to, because all affine transformations in general are too permissive physically. They don't necessarily mean anything. And moreover, we want to do the same thing for affine relations. So refine, put some structure on the objects. And on the morphisms, we want them to capture some notion of like permissible flows of particles, different non-deterministic behaviors, which are allowed in physics. And then at the end, I will like give this graphical language, these equations in terms of string diagrams, which captures these categories, this category which I'm trying to describe. Okay, so this is now the brief overview of Hamiltonian mechanics. So in Hamiltonian mechanics, what physicists will do is they will take the positions, the space of positions to be a smooth manifold, usually over the real numbers. So the idea is that a point on this manifold is a position, say, of a particle. And then what they will do is they will take the cotangent bundle of this manifold, and they call this phase space. And the idea now is that a point in the cotangent bundle is a position and a momentum of a particle together. Yeah, so a particle, and they use Q for position and P for momentum, which confused me for a while because I thought P would be position. No, I don't know why. So a trivial example, which is actually the one that I care about, will be in Euclidean space. If you take the cotangent bundle of Euclidean space, what you get is up to like a non-natural isomorphism Euclidean space of twice the dimension. But I find this example kind of hard to think about because it's like very degenerate. Why do you have to take the cotangent bundle? It's not very clear. So even though I don't care about the general case of manifolds, I only care about Euclidean space, I'm going to give the example over the circle, which I think is a bit more informative. And physicists would call this angular momentum. So the idea is you take your positions to be constrained to a circle. And when you take the cotangent bundle, this is interpreted as the space of positions and momentums. And in fact, you get that the cotangent bundle of the circle is the cylinder. It's the circle times r. So imagine physically you have some rigid pendulum. So there's like it's pivoting around this point in the middle. And this is the pendulum. And it can move around, be in different positions and have a different momentum. And if you look at all of the different configurations of the positions, the angle being the positions and the momentum being the magnitude of this arrow, then you find that this parameterizes the points on a cylinder. So for this example here, we have this angle, which gives you the angle of where this line is pointing up, the origin, and then the magnitude of this arrow is just how far up or how far down you are on this this cylinder. So for example, if you imagine this is like spinning this direction and the arrow is pointing up, if it were spinning faster, the arrow would be pointing even higher. And if it was spinning the other direction, the arrow would be down. So you can see that the different configurations of this pendulum, you can think of them as being points on this cylinder. So again, I only care about the Euclidean case, but I find it much easier to think of why is the cotangent bundle, why does it capture the positions and momentums of things? Because it's a bit less degenerate. Yeah, and then here is there's different ways which you can think of position and momentum in physics. I took this slide from John Baez, who took on his blog, who took this from some guy Adams' PhD thesis from the 80s, I think. So the point is, there's different kinds of notions of position in physics and consequently different kinds of notions of momentum. So if you're just in Euclidean space and your positions are just moving like in a line or on a plane or something, you'll call q your position, the derivative of q with respect to time, velocity, with momentum, and then the derivative of the momentum with respect to time is called force. And an angular momentum, the example I gave on the previous slide, the position is the angle. The derivative of position with respect to time is angular velocity. P is now angular momentum, and the derivative of momentum with respect to time is called torque. And for the next examples, the notion of momentum is usually doesn't have a nice name because Hamiltonian mechanics, I think, was like a more modern development in physics. So historically, they didn't really think of momentum very much. So in electronic circuits, you can take your position to be charge. The derivative of this is current, and then the momentum is like flux linkage, which probably people will have heard or often. But the derivative of momentum with respect to time is called voltage. And in hydraulics, you have volume, flow, and pressure momentum, which is just like a completely not very common name at all. But the derivative of pressure momentum with respect to time is just pressure, which is the more familiar notion. And in the thermodynamics, take the position to be entropy, the derivative of time with respect to time, entropy flow, and then the derivative of momentum with respect to time is temperature. Yeah, so the kind of core feature which I want to extract from the cotangent bundle is the symplectic structure. So in general, the cotangent bundle of a smooth manifold is a symplectic manifold, but what I care about only is Euclidean space, in which case the cotangent bundle is this vector space, and it has a bilinear form called the symplectic form. So the first definition, there's a bunch of technical conditions involving bilinear forms. So if you have a symplectic vector space over any field is a pair of a vector space, this bilinear form called the symplectic form, where the form has to be non-degenerate, alternate meaning, like I said, and a linear isomorphism between two symplectic vector spaces is called the symplectomorphism, in case this bilinear form preserves the linear isomorphism preserves the bilinear form. And The point why I don't really want to go describe all of the specific conditions of non-degeneracy and alternation is that in general you can just always work with a specific infinite dimensions, a specific symplectic vector space, where the bilinear form is just given by this formula. So, and the physically the idea is you take a position and momentum of say one particle, a position and momentum of the second particle, and then you take the inner product of the position of the first with the momentum of the second, and you subtract with the momentum of the first and the position of the second. So in if you take K to be R, say, and N to be 1, then what is this capturing is just the wedge product, which is you know, you have your 2 points. This is like P, this is Q. You draw this parallelogram. Your point PQ, your point P prime, Q prime, the symplectic form is just capturing the area of this parallelogram. So you can think of this very concretely without necessarily knowing about manifolds or whatever, as long as you're in the Euclidean case. Yeah, so now I want to motivate why is symplectic structure so important. And kind of the idea is that it allows me to take things that are required in Hamiltonian mechanics and then just turn them into nice algebraic forms, which are a bit less complicated. Yeah, so Hamiltonian mechanics, which I was alluding to earlier. That's why we care. So this is like the slide where I try to give a very, very, very brief overview of Hamiltonian mechanics. So what physicists call the Hamiltonian is a smooth function, which goes from the cotangent bundle of position space into R. So it takes any pair of positions and momentums and smoothly assigns to it a real number, which a physicist would call the energy. And if you take the d of h, then this gives you like a gradient on the cotangent bundle. And using the symplectic form, you get an isomorphism of vector bundles. And then if you compose these two things together, you take the inverse of this isomorphism and you apply it to d of h, you get what's called a Hamiltonian vector field. And the idea of this is if you take the exponential of this vector field, you get an automorphism on the cotangent bundle. So this describes some notion of time evolution. I'll give like some example on the next slide, but the idea is you have this function which describes energy, and then this gives you an endomorphism on the spaces of positions and momentum. So you can say after some time step, I have a position momentum in this manifold, and then it will just move somewhere else according to this. And everything is just governed by this Hamiltonian function, which assigns energies to positions and momentums. So this is all like differential geometry, very general, but I want to give a specific example because this is kind of hard to understand intuitively. Oh yeah, and also this Hamiltonian evolution operator is a symplectic morphism. So in a sense, if you forget about Hamiltonian everything, you can just work with symplectic morphisms, and this generalizes the equations of motion in Hamiltonian mechanics, and that's what I'm going to work with. Yeah, so here's my example. Take the Hamiltonian to be this function. So it takes position Q momentum P, and then it takes the sum of the squares and then multiplies by some angle theta divided by 2. This gives you the surface where the energy is on the vertical axis, position is here, and momentum is there. And then, of course, what we want to do is take d of h, and d of h gives you this gradient, and all of the arrows are just at any point are just pointing in the direction of the highest energy, so the steepest slope upwards. And then the Hamiltonian vector field, what I do is I take these points and I just kind of rotate them 90 degrees so now it's orbiting along the surface at points of the same energy. Because in physics, at least when there's no time dependence, everything has to preserve energy. So the idea is now that all of these paths that you get will be on the points. If you evaluate, if you take a path, if you take a point and you follow along the path, at any time you'll have the same energy level. So that's motivating this kind of notion of the Hamiltonian vector field. Now, if I project out this energy dimension, then I see that this is just a rotation on the plane. And in fact, if I take the exponential of this vector field, then this is just literally the linear map on r squared, which rotates by this angle of theta. And this example, actually, I think it's like the first example in Hamiltonian mechanics that undergrads would learn. And the idea is that this Hamiltonian describes like a ball on a spring. So as the position goes up and down, like in a sine wave, the momentum is in a cosine wave. And together it's a rotation because as the position goes further from the center, it kind of slows down and loses momentum. And momentum is the highest when the position is nearest to the center. So you have the position is like a sine wave like this, momentum is a cosine wave like this, and together it's a rotation. And the frequency at which it's oscillating determines the angle at which the angle which is like the speed that the spiral is rotating. Yeah, so hopefully this example can kind of serve to motivate why I care about symplectic morphisms, because I find all of this stuff with Hamiltonian mechanics and differential geometry a bit complicated. But if you just give up all of this and you just say, oh, I know that Hamiltonian evolution is a symplectic morphism, and you just, that's the only condition you care about, things become very simple or relatively simple. And again, I said I don't care about general smooth manifolds, just say r to the n. So in the case when your positions are in Euclidean space, then the space of positions and momentums live in Euclidean space of twice the dimension. And I'm not going to care about all of these Hamiltonian functions, just the quadratic ones. So it takes your v, which is your configurations of positions and momentums, and just applies it to this quadratic equation. So A is a symmetric matrix, B is a vector, and C is a constant. And kind of the higher dimensional version of the quadratic equation requires A to be a symmetric matrix and B to be a vector. So I'm going to ask that, given a quadratic Hamiltonian, that it is given Hamiltonian that it's a priori quadratic to make things simpler for me. Then if I do this like Hamiltonian evolution business, then I can show that it evaluates to this, and this is an affine transformation. So by requiring that this function be quadratic, then I get this is affine rather than some smooth function, so it's very well behaved. And back to this example, say if you were to choose to add some displacement by position A and momentum B, and you take, this is a Hamiltonian, or this is a quadratic function. If you do all this business to get this Hamiltonian evolution, this is the affine symplectic morphism, which takes a point in the plane and then just rotates around that point by the angle of theta. Okay, so the point is that I'm going to give up talking about Hamiltonians and just shift straight to the symplectic morphisms, because that's actually much more well behaved and that's what I need. So that's kind of the generalization of affine transformations, or the restriction of affine transformations to the one which preserves these nice physical properties. I'm going to use the symplectomorphism, the affine symplectomorphisms, but also I want to take my notion of affine relations and restrict them in a similar way. I have to talk about subspaces which are well behaved with respect to the symplectic form. So say that a linear subspace of a symplectic vector space, given a linear subspace of a symplectic vector space, the symplectic complement is just like the orthogonal complement, except instead of using the inner product, I use the symplectic form. And if you have an affine subspace of a symplectic vector space, say that it's an affine Lagrangian subspace in case the linear part is self-dual with respect to the symplectic complement. So if you just take the orthogonal complement, asking for something to be self-dual, it's like extremely degenerate, but for when you take the symplectic vector space and take the complement with respect to the symplectic form, then asking for self-duality actually gives you quite interesting things. In particular, if you take an affine symplectomorphism, which I said generalizes the equations of motion in Hamiltonian mechanics, you take the graph of this affine symplectomorphism. This is this subspace of the symplectic vector space, and in fact, the subspace is affine Lagrangian. So this is going to serve as the more kind of restrictive notion of an affine subspace, which preserves physical structure, which we care about. So now I can build a new category where the morphisms are these affine Lagrangian subspaces. Again, the objects are natural numbers, but now the morphisms are these affine Lagrangian subspaces of k to the 2n plus k to the 2n. So this 2 is coming from the fact that every object kind of expresses not only the position, but also the position and momentum paired together. And all of the structure of this category is basically the same as for affine relations. The composition is given by relational composition. The identity is just the diagonal subspace again. The monoidal structure is just given by the direct sum. So if you believe me that affine symplectomorphisms generalize these equations of motion of mechanical systems, or quadratic mechanical systems, then these affine Lagrangian relations generalize kind of the non-deterministic ways in which particles can flow. So if you have a morphism from n to m in affine Lagrangian relations, this is like kind of giving you constraints in which n particles can non-deterministically flow into m particles. Yeah, so now, again, I'm going to give generators. So now that I have generators for affine relations, I can give generators for the affine Lagrangian relations in terms of affine relations. So there's just two families of generators for affine Lagrangian relations. You take any two elements of the field K, and you just kind of take these sliders and label the sliders with these elements. So one for the gray one and one for the white one. And then you interpret this as an affine relation by kind of doubling things. So you have now all of your wires for position up here and all of your wires for momentum down there. And you demand that all the positions are equal, and you sum the momentums together here. And then you take the position, you multiply it by b, and then you add it by a to the momentums. And for the other color, you just do the dual thing. So we can eliminate some of the other generators in this setting. It's like very nice that it's generated just by these two classes of spiders. So we can kind of think of the morphisms as these labeled colored graphs. And to give some idea what's going on, if we just take a spider with one input leg and one output leg of color gray, labeled by AB. This is the graph of this affine symplectomorphism, which shears the position by B and then adds the position A. And this guy here in the different colors shears the momentum by B and then adds the momentum A. So these generators are kind of like things which together shear and then add affine shifts. And when you have multiple inputs and outputs, it's just adding different constraints. Yeah, and then now I don't expect you to understand the slide, but this is took a lot of work to prove this. That this category of affine Lagrangian relations can be presented in terms of those generators, which I described on the previous slide, and a bunch of equations. So if you have these two spiders and they're connected together, then they fuse into a new spider, and then you sum the arguments pointwise, for both colors. If you apply a new permutation on the wires, it doesn't matter which order the wires are coming up. And then we define these like box generators, so that for any element of the field, you have this box labeled by the element of the field. And if it's one, what this is the symplectic Fourier transform. And basically what this equation here is saying that if you take the Fourier transform of positions, this is momentums, and vice versa. Yeah, and this kind of thing is like, you have, if you take Z to be 1, then this is decomposing Z. The Fourier transform is just a 90-degree rotation in R2. And this kind of thing is saying like, you can decompose rotation into 3 shearing operations. And I argue that this is a useful thing to study and to find this equational theory, because you can describe circuits in mechanics just using these pictures and rewriting circuits. Because in reality, if you have like a circuit, you don't think of it in terms of its algebraic structure, but rather there's some geometric thing going on, like you have a wire that's connected to a component and so on, you wire things together. So this is kind of more close to physically how we think about circuits. So here's an example of electrical circuits. The idea is if you take a point in phase space, then this is a particle with a position and momentum. So any point in R2, I'm going to think of as this automorphism, which shifts the position by Q and the momentum by P. And in this case of electrical circuits, the derivative of the position with respect to time is interpreted as current, and the derivative of momentum with respect to time is interpreted as the voltage. And these kinds of black spiders where there's no label, so you're shearing by 0 and shifting by 0 implicitly. And you interpret these as idealized junctions of wires. So you take wires and you like solder them together with so many inputs and so many outputs, and inputs and outputs, and you think of this as a wire. So in this graphical calculus, you can like think of how the different possible ways in which particles flow through wires in electrical circuits. So you have some particle with position Q and momentum P. Then these equations, which I gave on the previous slide, dictate the different possible ways they can flow. So for example, you can, the point is that the position is always copied, but the momentum can go in different directions as long as the sum is the same. So you can take this particle and non-deterministically you can turn into 2 particles which have the same position, but here there's this one has lost its momentum on the bottom, and this one has retained all the momentum. Or dually, you can put all of the momentum on the second wire and have none on the first. Or you could take really any convex combination of the two. So here I've just said, okay, you think of the particle, goes into the wire, and it kind of splits into 2 particles with the same position, and the momentum is halved. Yeah, so one way to think of this is, you can think of this also in like hydraulics. You have like a pipe which splits into 2 and is very simplified, so there's no turbulence or anything. And as water flows through the pipe, the volume remains the same, but the pressure is like split between the 2 pipes. And so there could be like, if one pipe is like a different size, you could have more pressure in the first and less in the second or so on. But the point is that the pressure has to be, the sum of the pressures of the two pipes has to be the same as the original pipe which it branched from. And yeah, so that's talked about. You have particles and wires. You can also talk about, say, something like a resistor. So if you take like a very, very oversimplified view of a resistor, where a resistor doesn't generate heat, which is not the case in reality, but physicists and engineers often pretend as if it is because it makes calculations a lot easier, then the Hamiltonian function is given by this quadratic. And you interpret this label R as being the resistance of your resistor. And when you compose two resistors in sequence, then the resistance is sum. Whereas when you compose them in parallel, you have this more interesting behavior. So the idea is I take a wire, I like split the wire into two wires, and I put a resistor on the one and another resistor on the bottom with resistance R and S. And then I take the two wires and then bring them back together. So you can really think of this diagram on the left as like the physical implementation of an electrical circuit. Then I can rewrite this thing by taking the Fourier transform, which changes the colors and inverts the resistance, which is one of the equations I had. And then now that everything is the same color, you fuse them together and add all of the things. And now you have like this kind of Fourier transform resistor. So what you're going to do is take the Fourier transform again and change the color. And now you have something which you can interpret as a resistor. So you can derive from these equations. You have this one implementation where you have literally two wires that's put together with two resistors, with one resistance R and one resistance S. And this is the same as like the physical circuit where you just had a single resistor now, where the resistance is 1 over R plus 1 over S. So the point is that kind of, even though there's some non-deterministic behavior here, for example, like where this is the wires behave non-deterministically, in the end you get that you end up with a deterministic affine symplectomorphism, which is like a reversible thing. And using the pictures, really, this is how you would think of a circuit. You like have a physical, like 3D space, you have wires and resistors and so on, and you want to show that things are equal. Whereas if you just thought of things in terms of the algebra, then you lose kind of the geometric structure of how things are laid out. And in my opinion, sometimes it's harder to work with the algebra because you lose this kind of intuitive idea of what's going on with the circuit itself as you would think of it in real life. And I want to give a very, very brief example, which was my original motivation. If all of the stuff with Hamiltonian mechanics, I said I'm going to work in Euclidean space over the real numbers because of the stuff with manifolds. But in fact, if you replace R with the finite field of order P, for P and odd prime, then these affine Lagrangian relations embed into finite dimensional Hilbert spaces where the monoidal product is the bilinear tensor product and the monoidal unit is the complex numbers. So long as afterwards you quotient by invertible scalars. So this embedding on objects is going to send your natural number to the group algebra for the complex vector space where the basis elements are elements of Fp to the n. And in like quantum information, the morphisms from 0 to 1, they're interpreted as what are called stabilizer states. The general morphisms from n to m are interpreted as like stabilizer circuits. The isomorphisms from n to n are interpreted as Clifford operators. So the general idea is, because we've done all of this stuff in enough generality, we don't care about which field we work with. We have a lot of liberty to change kind of the setting we're working in. And if you do it over a finite field of order P, you have the same kind of picture as in classical mechanics, where now your Hamiltonians are just quadratic forms. The Clifford operators are these are these linear operations between complex vector spaces. And in phase space, this is the same as an affine symplectomorphism. So there's like three equivalent ways of working with things. And this language I described in this setting where you choose the field to be FP, it's called like the stabilizer ZX calculus, and it's used by people to do essentially calculations in quantum information. And yeah, this is my motivation to kind of find the mathematical semantics of what's going on in quantum information, because the stabilizer stuff is extremely important in quantum error correction and kind of forms the basis of all of quantum error correction. So kind of find the precise mathematical formulation and generalize it. That was my motivation. Yeah. And then yeah, we've generalized this to Gaussian quantum mechanics, where the particles are not points but Gaussian distributions. We've had time dynamics. We have a lot of people have reformulated other aspects of mathematics using string diagrams. So this is like an open area of research where you take something in mathematics and you try to reformulate it in terms of generators and equations. So talk.
Any brief questions? We should probably leave soon, yeah.
We can ask questions, but call in the hallway.
Yeah,
Yeah, sorry, I just, got started as well.
that's all right.
Can I end the session?
Yeah.
Bye, everybody.